Dear friends, let me present to you the Institute for Nanoengineering in Electronics, Spintronics and Photonics of MEPhi. I bet you already have a lot of questions. What NESPI is about? What would I learn if I come to study here? And finally, what do all these words like photonics or spintronics mean? Don't worry, in this talk I will gladly answer these questions and more. Modern electronics faces many new challenges. Data usage increases with terabytes upon terabytes of new information every month, which needs to be transmitted, processed and stored. It is a similar case with energy consumption or simply electric power. It's not just oil and coal, folks. Turns out that electronics is important here as well, from solar cells to AC-DC converters. And finally, health and safety concerns of the human race require a lot of novel electronic devices for security systems, medical equipment, as well as environmental monitoring. Clearly, these challenges can't be met just by scaling the same technology again and again. The possible solutions include creating new chemical compounds and nanomaterials, designing novel electronic components with different architecture, and finally, using completely new physical principles such as spintronics or magnetic electronics, and quantum computing. Let's overview the development of modern electronics as a technology. One of the most important benchmarks here is the so-called gate length, usually the smallest part of any transistor. Reducing this length not only allows us to increase the speed and performance on, say, a microprocessor, but also to put more and more transistors on the same area, making microchips cheaper and more complex. This is the essence of Moore's law. The number of transistors on a microchip doubles every 2 years. It's all about the scaling. But what is a transistor, you may ask, and why is it so important? Well, see, transistors are relatively simple semiconductor devices, which have two basic functions: amplifying electric signals or switching between on and off states. The first function is used in, you guessed it, all sorts of amplifiers, for example, signal transmitters in our mobile phones. The second function makes the transistor a logic gate, which is the basis of all the digital electronics, such as CPUs and GPUs. In fact, NVIDIA was one of the first companies to order the latest generation of 7nm transistors for their video cards. Now that we all agree that scaling of transistors is important, the question is, how small can we make the gate length? Turns out, there are important physical limitations preventing infinite scaling, the most obvious of which is the distance between the atoms in the semiconductor crystal. It's about 0.5 nanometers. But let's not forget that it's not just about whether or not we can make something, it's also about the cost. Before we approached 22 nanometers, the cost of one transistor scaled down exponentially, another side effect of the Moore's law. Beyond that, it stopped scaling so well, because the technology had to become more and more complicated. This is where the new architecture comes forward. When we can't make the same device but smaller, we have to invent a whole new and different design. This is what happens now as we move to 7 nanometers and smaller. What will happen after 3 nanometers, nobody knows. When it comes to new materials for electronics, it would be remiss of me not to mention graphene, probably the most popular nanomaterial. Graphene is simply a single layer of carbon atoms arranged in a honeycomb structure. It can be rolled up into carbon nanotubes. Surely you've heard of the Space Elevator project. But also, graphene has extremely high electrical and thermal conductivity, which makes it a perfect material for a new generation of electronic devices. Quantum computing is a completely new way of processing information. Instead of the usual bits, which can be in either on and off states, corresponding to 0 or 1 respectively, quantum computers use qubits, which can magically exist in a superposition of both states at the same time. This is the most efficient way to do parallel processing. Qubits can be based on defects on diamonds, photonic circuits, nanocrystals, or ion traps. The downside is, all these technologies are very complicated, and so quantum computers only exist in laboratories so far and contain at most a few dozen qubits. It does not mean that we won't hit the market in a few years, especially since large companies such as Google put a lot of resources into development in this area. While electronics is based on electric currents, physically moving the charge from one point to another, let's not forget that electrons also have spin. Spin means that the electrons behave like small magnets, which have a north and south pole. This allows us to manipulate charge currents with magnetic field, creating spin-polarized currents, but we can also use pure spin waves, rotating electrons in accord without moving them. Spin currents don't produce heat and so are very energy efficient. Spintronics is already used for data storage. It turns out that the good old hard drive is a spintronic device. Photonics is a word you are probably more familiar with. Photons are particles of light, each carrying a quantum of its energy. Eyes are our main source of information, so it's not surprising that light has been used to carry signals for centuries. In recent years, optical fibers has connected with whole world, offering fast, efficient and safe way to transmit data over great distances. But photonic devices can also process and store data, so fully photonic computers are possible. With nanotechnology, it's also possible to create photonic crystals, special materials for controlling and storing light. As a final example of photonic technology, let's remember CDs and DVDs. Now that you are all up to speed on the advances in electronics, you are probably thinking, but what does your institute actually do? What's so special about it? You see, my dear friends, NESPI is a unique assembly of departments dedicated to fundamental solid-state physics, nanotechnology, and applied circuit design. Unification of these fields is the best and only way to be competitive in modern electronic industry. MEPhi has long-standing expertise in both condensed matter science and circuit engineering. The latter includes special applications such as space satellites and particle accelerators. NESPI has a number of international collaborations in the emerging fields of two-dimensional nanostructure, composites, and ion cluster technologies. The nanoelectronics research is supported by an extensive range of equipment at MEPhi Nanocenter. It contains a full production line for electronic components such as transistors, diodes, modulators, sensors, and so on. The research carried here focuses on novel devices and technologies, which are designed, modeled, and implemented, resulting in a working prototype. This new technology is then transferred to our industrial partners. NESPI students have a unique opportunity to get hands-on experience working with full-scale equipment and learning key methods for electronic and material science industry. These include epitaxy, lithography, plasma-enhanced deposition, to name a few. We offer a range of unique bachelor's degree programs in the areas of applied mathematics and physics, electronics and nanoelectronics, as well as photonics and optical informatics. This allows our students to pick the track best suited for them, be it physics research, modeling and simulation, or applied science and technology. The titular Nanoelectronics, Spintronics and Photonics program is available in English. Master's degree programs at NESPI have a similar scope to bachelor's programs, but are more advanced. We welcome both NESPI graduates and bachelors from our universities with suitable background. We also offer additional courses for those students who need to catch up on or refresh certain subjects. Note that for master degrees, we have the new Microwave Photonics program also available in English. We also have a wide range of postgraduate programs in the fields of physics and astronomy, informatics and computer engineering, as well as electronics, radio engineering and communication systems. NESPI has a lot of partners among universities and industry, both in Russia and abroad. Our partner activities include scientific collaboration, R&D projects, double degree programs for student and student exchange opportunities. Well, thank you for your attention. We'll be happy to see you at NESPI this year.